Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 4, More Functions, More Features, Lesson 6, Well Versed. We are going to be starting with the ready section. However, we're going to be skipping the first couple problems here. And the first assigned problem is going to be number 5. So here are the directions for 5. Describe the transformations that will need to occur to the graph of the parent function so the result is the function described. And for number 5, our function is r of x equals parentheses x plus 3 squared minus 7. So hopefully we can recognize this as a quadratic. Not actually necessary in order to answer this question. So if you did not recognize that this was a quadratic, it doesn't mean that you're going to get the question wrong. However, at this point, given the work that we've done with quadratics, it actually would be really preferable if you can recognize that this is a quadratic function. So the parent function for quadratics is p of x, or any letter of x. I'm just going to use p. P of x is x squared. And it's a very basic quadratic. And the question is, what essentially happened to the parent function that has resulted in r of x, which is not x squared, but x plus 3 squared minus 7. And you can see that essentially two things have happened. You got this plus 3, and you got this minus 7. Those are the two modifications that we are being tasked to describe. So looking at I'll just go ahead, I guess, move this for a second. Okay. So for number 5, looking at the two things that have happened here, from the parent function, if we start with the parent function, we have replaced x with x plus 3, right? So the entire thing is being squared. It's not just x, so it's not x squared plus 3. But we've replaced the x with x plus 3, and now we're squaring that. And then we've slapped this minus 7 at the end. So whenever you have an x plus 3 like this, that is a horizontal shift. So it's either being shifted left or right. And when you have a number at the end, like in this case just minus 7, just kind of hanging out doing its own thing, that is a vertical shift either up or down. So let's just get that into words here. So the transformations that have happened from the parent function to r of x is that we can translate left 3 units. And it's left because it's plus 3. So when your horizontal shift, when it's plus a number, it means you've been shifted to the left. And when it's minus a number, it's been shifted to the right. So we can translate 3 units. Left 3, actually we don't even need the word units. We'll just say translate left 3 and down 7. So to go from the parent function to r of x, we would translate left 3 and down 7. Question 6. Again, recognizing the type of function here is not strictly necessary, although, again, hopefully just by looking at it, we can tell that this is an absolute value function. It has absolute value in it. And for our purposes, the parent function here, again, we'll just say p of x, is simply the absolute value of x. You could think of that as sort of our starting spot. And then the question becomes, well, what again were the modifications, what were the translations, or whatever it was that we did to the parent function that has resulted in f of x equals absolute value of x minus 8 plus 14. This is actually very similar to 5. It doesn't really, quote unquote, matter that it's an absolute value versus a quadratic. The translations are very similar. So again, just like with 5, we have a horizontal shift that's really impacting x directly. We've replaced x with x minus 8 in our parent function. And then also like 5, we have a number at the end, this plus 14, and that is a vertical shift. So if we want to describe that, we can say that from the parent function, we can translate right 8 units and up 14 units. So we are translating right because with a horizontal shift, when it's a negative number, so when it's minus 8, that means that we are going to the right. And for the vertical shift, it's plus 14, which means we're going up 14. Question 7. I'm not going to write it this time, but for 7, this is clearly an absolute value function. And it is once again going to be, it's going to be very similar to 5 and 6. There's going to be one sort of new thing. Now, the order that we sort of describe these transformations, the order actually does matter, right? The order does matter. And the order that we describe these things in, maybe I'll just do this, I'll do this in red over on the right. So for our purposes, I think we've really only looked at like 3 or 4 different kinds of transformations. The first thing that you need to talk about is you need to talk about any kind of horizontal shift. Okay? Horizontal shift. That has to be the first thing. Occasionally, this is called a phase shift. When you start to get into trigonometry, you may end up seeing that phrasing of phase shift. It's the same idea, just like left or right, essentially. After you've sort of addressed any kind of horizontal shift or a phase shift, then you need to talk about any kind of stretching or shrinking or flipping. All right, and you can do those like if it's both stretched and flipped, you can do those as 2 separate steps, or you can say them as 1 step. And then the third thing is any kind of vertical shift that you may have. Okay, so you have to go in that order. So for 7, the first thing we're going to talk about is the horizontal shift represented by x plus 5. The second thing we're going to talk about is the stretching that is reflected by the 2. And then the third thing that we're going to talk about is the vertical shift of minus 20. Notice that the order here, it's sort of like the order of how these things impact x. So if you take a look at the equation, x, like let's say x is, 1. Well, when you plug in a 1, the very first thing you would do is 1 plus 5. So that's the first thing that happens to x. Then you find the absolute value, whatever, and then you multiply by 2. That's the second thing that you would do. Then you would subtract 20, which is the third thing that you would do. So the order that you describe these things is sort of the order in which they are applied to your input of x. Let's go ahead and describe what's happening here. So the first thing that we have to talk about is that horizontal shift of x plus 5. And as we've now seen several times, when you have something like x plus 5, when you're adding, it means it's going to be a shift to the left. So the very first thing that happens is we translate left 5 units. Okay, so we translate left 5 units. We could say dilate is one way to describe the sort of what's happening here, or you could say stretch kind of means the same thing. Dilate or stretch. by a factor of 2. Okay, that's the second thing that happens. And then the last thing that happens is we translate down 20 units. That is our vertical shift, and that happens at the end. And if we do that to the parent function, we will get g of x. Question 8. 8 is a quadratic, so we have taken our parent function of x squared, and we've replaced the x squared. We've replaced the x with x minus 12. We've also introduced a coefficient on the squared term. It used to be 1, now it's negative 3, and then we've had a vertical shift there at the end. So let's go ahead and describe all that. Again, the very first thing that we have to talk about is the horizontal shift, which is x minus 12. When you're subtracting the number, it means you're shifting to the left, and so the very first thing. Oh, no, I'm sorry. When you're subtracting, it means you shift to the right. When you're subtracting, you shift to the right. So the very first thing that happens is we translate right 12 units. Okay? That's what's represented by the x minus 12 as a horizontal shift to the right. Then we have to talk about the negative 3. And we can describe that either as a dilation or a stretching. So we either dilate or stretch by a factor of negative 3. Now, I guess you could leave it like that. You could say negative 3, but it might be worth just sort of clarifying that that reflects the graph downward, right? So when you dilate or stretch by a negative number in this context, not only are things going to become more steep, right? That's what the 3 does. But it's also going to flip it. That's what the negative does. So you could either say this is like two different things or one thing. It's kind of this. They happen almost like instantaneously, I guess. And then the last thing that happens is, and then we translate up 32 units, and that represents our vertical shift. And that's how we get h of x from our parent function. Moving on to the set section. Directions here say, find the equation of the inverse function for each of the given functions. So our first problem is number 9. We're told that r of x equals 3x plus 7. This is a linear function. I think we saw a couple different strategies for how to do this in the lesson. One of the strategies was sort of looking at how a function is essentially built, like what's the process of building that function, and then to get the inverse of that function is to sort of go in the opposite order, right? So, for example, in this equation, we're taking x and we're multiplying by 3 and then adding 7. And if we want the inverse, we basically do the opposite in the opposite direction. So the last thing we did was we added 7. So if we want to, we could get the inverse by starting by subtracting 7, then doing the opposite of multiplication, which is division, so we would divide by 3, and that actually would work. However, I think it's going to be a little bit easier for these problems if we adopt another approach, which is to simply, we're going to just swap our input with our output. So we'll introduce y just to keep things simpler. We're going to introduce y, and then we're going to swap x and y, and then we're going to solve for y, which used to be x. Let's take a look and see what that looks like in case everything I just said was confusing. So the first thing that we're going to do is we're just going to sort of set up this equation to be manipulated a little bit. I'm going to do two small things that I think are going to help us. The first thing I'm going to do is I'm actually going to change the order of the equation. So the equation starts with r of x, and then it says equals 3x plus 7. I'm actually going to bring that 3x plus 7, I'm going to bring that over to the left. I'm going to say 3x plus 7 equals. And then the second thing that I'm going to do in this sort of step 0 is instead of saying r of x, I'm actually going to just get rid of function notation and say y. I don't want to keep r of x as my variable while I am sort of algebraically manipulating this equation. So I'm going to use y instead. And then at the very end, when we give our final answer, it's going to be we're going to use function notation again, so it's going to be r inverse of x. Okay, but for right now, let's not use function notation and just say y. And I also swapped the equal sign here. And the reason why I swapped the equal sign is because what we're going to do now is we're going to switch x and y. Right? So we're going to change our equation. We're not really going to like do any algebra, but we're literally going to, wherever we see the x, we're going to put the y, and everywhere we see the y, we're going to put the x. So our new equation is 3y plus 7 equals x. And again, we didn't really do any algebra here. We didn't like add, subtract, multiply, divide, but we just sort of manually changed our equation and we swapped the x and the y. And now what I want to do is I want to solve for y. So I have a y, it's on the left, and I want to get that y by itself. I want to get y equals. And that's going to give me my inverse function. So I have to deal with the 3 and I have to deal with the 7. First thing I have to deal with is the 7. So we're going to subtract 7 from both sides. And that gives me 3y. That cancels. Equals x minus 7. If I want to get y by itself, I have to get rid of that 3. And it's 3 times y, which means to undo it, I want to use division. I want to do the inverse of multiplication. So I'm going to divide everything by 3. And the 3 that was on my y goes away, and I get y equals, which is nice because that's what I want. Now, what we have here is we have x minus 7 divided by 3. And I'm actually comfortable leaving it like that. If we wanted to, I'll do this in red, and this part is optional, what I'm about to write. If we wanted to, we could express this as in slope-intercept form if we wanted to. And if we did that, this becomes 1/3 x minus 7/3. We essentially break up our big fraction into like two small fractions. And because the coefficient on x is a 1, that causes the coefficient, 1 divided by 3 is 1/3. And then we get the 7/3. I don't think that's going to be necessary for this problem. Okay, so this is this is extra right here. But in a different context, you may find it helpful to express your answer in slope-intercept form because it is used a lot. And so that's what that would look like if we were to express this linear function using slope-intercept form. But I think we're safe to leave it the way that it is right now. And so our final step here is to just reintroduce function notation. So our original function was r of x, which means our answer now is r inverse of x. Okay, that's replaced the y, and now we're just going to write our function, which is x minus 7 over 3, and that is our final answer. That is the equation of the inverse function that would essentially undo what our original function did. Next question is 10. This time our equation p of x is x squared minus 5. This is a quadratic. And we are limiting our domain. Uh, in the original function, quote unquote, normally x could be anything you want. X could be positive, negative, 0. It's a quadratic. It doesn't really matter. For this question specifically, we are restricting our domain so that x is strictly positive. So x is not 0 and x is not negative. And the reason for that is because, as I think we saw in the lesson, the inverse of a function is not always a function, and we want it to be a function. And so when that happens, we have to restrict our domain of the original function so that when we find the inverse, we still have a function. So for number 10, we're going to, our step 0 here, just to sort of set us up to be able to do this problem, is I'm going to flip my equation. I'm going to say x squared minus 5, just bring that to the left, equals p of x, except I don't want to use function notation while I'm manipulating this equation, so I'm just going to say y. It's just easier just to have like a quote normal variable as opposed to like doing things with function notation. So I've flipped my equation and I've removed function notation. I've introduced y. And now what we're going to do is we're not going to do any real algebra. We're going to create a new equation, and we're going to flip the x and the y. So everywhere I see an x, I'm going to put a y, and everywhere I see a y, I'm going to put an x. So that means this equation becomes y squared minus 5 equals x. This is our inverse. Now, in order to make this like a usable function, we need to isolate y. Otherwise, it doesn't really do us much good as a function, because with a function, you want to be able to plug in something and get your output. Right now, our output is crowded with a whole bunch of stuff. So we have to get y by itself. So in order to get y by itself, we have to deal with the squared, we have to deal with the minus 5. First thing we want to deal with is the minus 5. The inverse of subtraction is addition, so that means I want to add 5 to both sides. When I do that, the 5s go away. And on the left-hand side, I'm left with just y squared. And let me just redo that so it's not a mess. So we have y squared equals, and on the right-hand side, we have x plus 5. So I'm just going to say x plus 5. The only thing preventing y from being by itself right now is the squared. So I need to get rid of that. In order to undo the inverse operation of squaring is square root. So I'm going to take the square root of both sides. By doing that, on the left-hand side, the square root of y squared is just y. So I have isolated y equals. Now, if this was, if what we were doing right now was just like pure algebra, and we weren't like, we didn't have our original function and the restricted domain and inverses and whatever, and if we were just sort of like manipulating this and just doing just like pure algebra, we would have to include a plus minus here because in the original equation, when you say y squared equals x plus 5, we don't know whether y was positive or negative. And so in order to account for that fact, we say that, all right, well, y could be positive whatever, or it could be negative whatever. However, in this problem, because we're talking about functions and things like that, with a function, you can't have plus minus in a function, right? So y equals plus or minus. That violates the whole idea of what a function is. Remember, with a function, you want to be able to plug in an input and know what your output is every single time. Well, if your function has a plus minus in it, you're introducing some ambiguity. You're saying, all right, well, maybe it's plus, maybe it's minus. I don't know, it's both. That doesn't work with a function. So this would be a problem, the plus minus. However, our original question restricted the domain. and said that here the domain is that x is strictly positive in my original function. And as I think we saw in class, that doing that allows us to actually ignore the plus minus and leave this as just, we'll do it in green, and leaves us with just the square root of x plus 5. Right? So it's kind of a long-winded way of saying it's just positive square root of 5, not negative square root of 5, because we restricted our domain in the original function. We are basically done this problem. The only thing that we, quote unquote, have to do is sort of just express this using function notation. So the original function was p of x, which means my inverse is going to be p inverse of x is the square root of x plus 5. And that is my final answer for 10. That is the inverse function for p of x. Number 11, we're told our original function is f of x equals x plus 9 over 2. This is a linear function. And just like the last couple questions that we've done, the first thing I want to do is I want to bring my x plus 9 over 2 to the left. And that's going to equal f of x. I don't want to use function notation while I am doing the algebra here, so I'm just going to say y. In order to make this the inverse function, it means I want to swap my x and my y's. I'm basically creating a new equation. I'm not manipulating the old equation. I'm just coming up with a new one. And that new equation is the same one as the old one, except I've swapped my x and my y. So that means my new equation becomes y plus 9 over 2 equals x. I want to get y by itself, and I've got a 9 and a 2, and it's going to make our job a lot easier if I get rid of that 2. So let's get rid of that 2. The 2 is being divided, and it's dividing into the entire thing. It's dividing into not just y, but y plus 9. Because 2 is being divided, the inverse operation, the thing that will undo that, is multiplication. So I can take my entire equation and multiply everything by 2, the left and the right. When I do that on the left, the 2 that I'm multiplying is going to cancel with the 2 in the denominator, because again, that 2 is being divided into everything on the left-hand side, not just the y, but the y plus 9. So the 2's cancel, and I'm left with just y plus 9 on the left-hand side. Anything I do to the left, I have to do to the right. So I'm going to multiply the right by 2. So 2 times x is simply 2x. And the rest of this is pretty straightforward. I'm going to subtract 9 from both sides to get y by itself. So that gives me y equals 2x minus 9. And to express my answer using function notation, my original function was f of x, which means the inverse is going to be f inverse of x. It's going to undo whatever f did. And specifically, it's going to be 2x minus 9. That's my inverse function for f. Question 12. 12 says h of x equals x squared plus 6. That's a quadratic. And just like number 10, we are restricting our domain such that x is strictly positive. And as we saw with 10, the reason why we're doing that, the reason why we're restricting our domain is that sometimes, and with a quadratic you have to do this, if you just do the algebra and you don't, well, long story short, it introduces a plus minus into your inverse, which is no good with a function. You cannot have a plus minus in a function. It violates the whole idea of what a function is. So in order to get around that, we have to sort of somewhat artificially restrict our domain so that our inverse is also a function. And like I said, with quadratics, that comes up. Comes up actually with any even function, quadratics, fourth power, sixth power, et cetera, et cetera, et cetera. So as we've now seen a couple times, our sort of step 0 is to bring the right to the left. So this becomes x squared plus 6. And then also it's just easier if we get rid of function notation temporarily and we just go back to using y. To get my inverse equation, we simply swap my x with my y. So x squared plus 6 equals y becomes a new equation, y squared plus 6 equals x. And I want to get y by itself. So the very first thing I want to do to get y by itself is subtract 6 and subtract 6. So that cancels, and on the left, I'm left with just y squared. And on the right, I have x minus 6. To get rid of a squared, we want to take the square root of both sides, square root and square root. The square root of y squared is y. And because we restricted our domain, we do not need to include the plus minus here. The sort of pure algebra normally would require us to have a plus minus in front of the second square root here. But because we've restricted our domain, we don't need that, and we can just simply say square root, sorry, might as well have the whole thing in green at this point, just square root of x minus 6, which is a function. And last step is to just reintroduce function notation. Our original function was h of x, so our inverse is going to be h inverse of x, and that is going to be the square root of x minus 6. That function will undo whatever h did, and if you plug in your output from h, you will get your input from h. That's what an inverse does. Question 13. 13 says k of x equals negative 2x plus 4. This is a linear function. If we bring the negative 2x plus 4 to the left, we replace our function notation with just a y. To get our inverse equation, we swap our x's and our y's. So negative 2x plus 4 equals y becomes a new equation, negative 2y plus 4 equals x. Notice that nothing else changes. We just swap the x and the y, but everything else is the same. Now we want to get y by itself, so I have to deal with the negative 2 and I have to deal with the plus 4. The first thing I want to deal with is the plus 4, so the inverse of addition is subtraction. So my 4's cancel on the left, leaving me with negative 2y on the left, and on the right we have x minus 4. The negative 2 is being multiplied to the y. The inverse of multiplication is division, so that means I want to divide everything, the left and the right, by negative 2. So here on the left, my negative 2's cancel, and I'm left with just y, which is nice, that's what I want. And on the right, we get x minus 4 over negative 2. Now, if we were to just go ahead and finish out this problem, before I get on my soapbox here, let's just finish out the problem. So to finish this, we just have to reintroduce function notation. So it was k of x, so that means the inverse is going to be k inverse of x, and then is just what we have, x minus 4 over negative 2. All right. And if that's your answer, that's fine. All right, that's fine. It's a little bit better, and this is maybe a little bit extra, but I do think it's worth just mentioning briefly. It would be a little bit cleaner, just a little bit. I'm not in love with the fact that we have just a negative 2 in our denominator. It's not like a problem, but it kind of irks me, I guess, and would irk maybe some other people as well. So one way to sort of deal with that is if you take your fraction here, and if we simply just multiply everything by -1 over -1, right? So if we just sort of take everything and change our signs, right? We're allowed to do this because, this number here is just 1, right? So -1 over -1 is 1, and when you multiply by 1, you don't change anything. So if we do that, we get k inverse of x equals, if you change all of your signs in the numerator, you get -x plus 4, which is simply 4 minus x. And then in the denominator, it's no longer -2, but it's plus 2. And really, that's better, right? That's a better version of our answer. If you put the first one, it's fine, right? It's really not a problem, but sort of like if you want to make it sort of as clean as possible, I'd say that the second one's preferred, just because like having a negative by itself in the denominator is like a little weird. So, but again, either version would be fine for this assignment. Number 14. I'm going to erase all of this from the last one because we don't need it anymore. All right. Number 14. 14 says g of x equals 1/2 x plus 9. This is a linear function, and we are looking for the inverse of this, which is going to be another linear function. So we bring the right over to the left. So this becomes 1/2 x plus 9 equals, instead of saying g of x, we get rid of function notation temporarily, and we just say y. To get our inverse, we keep everything the same, except we replace all of our x's with y's, and we replace all of our y's with x's. So our new equation becomes 1/2 y plus 9 equals x. And now we want to isolate y. We want to get it by itself. So I have to deal with the 1/2. I have to deal with the 9. We're going to deal with the 9 first. The inverse of addition is subtraction. So we're going to subtract 9 from both sides. That cancels on the left. So the only thing remaining on the left is 1/2 y equals x minus 9. And then the only thing left to do is to deal with the 1/2. Now, technically, this is 1/2 times y. We're multiplying, and the inverse of multiplication is division. So you could divide by a half, and that is mathematically valid. Dividing by fractions is kind of annoying, and so it actually would be great if you recognize that multiplying by 1/2 is the same thing as dividing by 2. And if you want to undo division, you multiply. So we can take this and just multiply everything by 2. It's going to get the job done the same way, and that way we're not dividing by a fraction, which is kind of, which can not necessarily be the easiest thing in the world. So when I multiply everything by 2, the 2 and the 1/2 cancel, and I'm left with just y. I guess we're still doing green here, aren't we? So we're left with just y, which is what we want. That's good. And I have to multiply everything by 2, so that 2 is going to get distributed to both terms on the right here. So 2 times x is 2x minus 2 times 9 is 18. So as predicted, we get a linear function here. So the original function was g of x, which means my inverse is going to be g inverse of x. And it's going to be what I just found, 2x minus 18. Let me redo that. Looks not great. So 18. And that is my inverse function for number 14. All right, we'll wrap this thing up with the go section. And we'll just dive right into number 15. So for 15, we are given an equation, c equals 2 pi r. And our directions here are solve for r. Well, it's not strictly necessary in order to answer this question. However, I do think that it would be really, really great if people understood the context of this equation. So it actually turns out that every single equation on this page, 15, 16, 17, and 18, well, 17 and 18 are the same equation. So every single equation actually has a geometric context. Okay, so 15, 16, and then 17 and 18. All of these are formulas that pop up in geometry. And it would be nice if we knew what they were. I just think it adds a little bit of context to what it is that we're doing here. So if you know what any of these equations sort of represent, that's great. If you don't, it's not a problem. Although 15 would be good to know. 15 would be good to know. All right. If you don't recognize 16, it's not like a real big problem. And 17, I think we're going to talk about 17 later. But if you don't know what 15 is referring to, it'll be advantageous for you to remember this formula, or at least be able to recognize it when you see it. So it turns out that for 15, this is the formula for the circumference. I feel like I'm going to spell that wrong, but I don't feel like checking. So if that's spelled incorrectly, I apologize. The circumference of a circle. Okay. So this is the formula for the circumference of a circle, 2 pi r. 2 is a constant, pi is a constant, it's approximately 3.14, and r in this case stands for the radius of the circle. So if you want the circumference, which is the distance around the circle, you can find that by doing 2 times pi times the radius of the circle, and that will give you the circumference. None of that is necessary in order to answer 15. However, I do think that there is value in recognizing it when you see it. So if you were not familiar with this formula before, you are now. And I would encourage you to just try to keep it in the back of your mind, because it does pop up from time to time. And in all seriousness, you may have an assessment at some point, standardized test or whatever, where you actually do need to know this formula. So it's not just for the sake of it, but there actually is, there are contexts where you would need to know that formula. Anyway, for 15. We want to take this equation, we want to solve for r. So this actually is not that bad. It's actually pretty straightforward. I want to solve for r, so I'm going to do my step 0 here and just sort of flip the equation. We got plenty of space here on the right, so I'm just going to do it over here. So if we flip our equation, we get 2 pi r equals c. We didn't really change anything, we just flipped it. Because it's just nice to have r on the left, because that's the thing that we're solving for. And in order to get r by itself here, I just have to get rid of the 2, and I have to get rid of the pi. But the thing is, I can actually do this in one step, because both the 2 and the pi are being multiplied to r, which means if I want to do this in just one step, I can just divide by both the 2 and the pi, right? I don't have to divide by 2, then divide by pi in like 2 separate steps. There's really no reason to do that. In this context, you might as well do it in one step and just get rid of both the 2 and the pi. And again, we can do that because it's the same operation. It's 2 times pi times r. It's all multiplication. So we can undo all of that multiplication with just a single division of 2 pi. And what we end up getting, so on the left-hand side, both the 2 and the pi go away, and I'm left with r, which, by the way, is what we want. It says solve for r, so that's great. On the right-hand side, we have c divided by 2 pi. I can't do anything with that, right? The c and 2 and pi, they're just, one's a variable, one's a constant, and one is a irrational, or actually transcendental number. There's nothing I can do with that, so it's just c over 2 pi, and that's my answer. So I do apologize spending multiple minutes with something that took about 30 seconds, but I do think that there was value in the discussion. 16. Question 16. My formula here, A equals B1 plus B2 over 2 times H. Again, as I referenced earlier, this has a geometric context, and if you know it, then that's great. We actually did discuss this in the old Math 1 curriculum, so if you recognize it, that's awesome. This formula is the area of a, do you know what it is? Trapezoid. This is the area of a trapezoid. So A is area, B1 is one of your bases, B2 is your other base, and H is your height. And if you plug this in, you will get the area of a trapezoid for number 16. So in order to solve for H, it means we want to get it by itself. As always, my sort of step 0 here is just to flip my equation so that the thing that I'm solving for is on the left. I've just found that it makes things a little bit easier. And it's like, might be a little annoying to introduce another step, but it's also like super easy. You just flip it, so it doesn't exactly require a lot of work. So we want to get H by itself. And actually, you know what, I'm going to, let me rewrite that. I'm going to move it a little bit to the right here. I want to give myself some space. So we end up getting, again, we get B1 plus B2 over 2 times H equals A. All right. I want to get H by itself. And for this problem, I'm going to solve it one way, and then maybe we'll solve it a second way, and I'll let you guys decide which way makes more sense to you, because there's pros and cons to both methods. So one way to get H by itself, you can actually do it in one step. Okay, so one way to do this is to do it in one step, and that one step is to recognize that what you're doing here in this equation is you're taking H, and ultimately at the end of the day, what you're doing is you're multiplying by a fraction, right? That horizontal line there is a fraction bar. So you're taking H and you're multiplying by a fraction, and that fraction, the numerator is a binomial, that's B1 plus B2, and the denominator is a constant, it's just 2. So if you want to get rid of it, which is what we want to do, right? Because we want to get H by itself. If you want to get rid of a fraction that is being multiplied by something, it's kind of a handy trick is to multiply by the reciprocal of that fraction. So again, what's inside the parentheses here, we're trying to get H by itself, and it's clearly not by itself. It's being multiplied by a fraction, and if we want to get rid of it, if we multiply by the reciprocal of that fraction, if we flip the numerator and the denominator, what's nice about this is, when we do that, we are going to be left with just H equals, right? So that's nice, right? We're actually almost done this problem because we've got H by itself, and now I just need to figure out what's going to be on the right-hand side. What's on the right-hand side is we're going to take A and we're going to multiply by this reciprocal, this 2 over B1 plus B2. And it's actually not out of the question that you could leave it like this. You could leave it like A times 2 over B1 plus B2. And that could be your answer. That's actually not a bad format for our answer. Kind of maybe equally valid, in my opinion, would be if you wanted to, you could take the A and you could kind of smush it into the numerator of your fraction, and that means you'd be left with 2A in the numerator, and then B1 plus B2, and this is still H. These are, mathematically equivalent for sure, and I'm not even really sure which one would be better. Kind of depends on the context that you're doing this in. Um, so those you don't have to say both. So you could say here. I'll even say or, right? So don't do both, but pick one and kind of go with it. That's our answer. Now, if that all makes sense to you, then you can just continue on to the next problem. But I'm gonna erase this now because I need the space, and I'm gonna erase this and that and that. All right. Um, a second way of doing this is to do it in two steps. And maybe this is easier, maybe it's more complicated. I'm not sure, but I think that there's value in sort of seeing it a second way. If you want to get h by itself, you could do this in two steps by saying, all right, well, the first thing I want to do is I want to get rid of that 2, which means what I could do is I could just multiply by just 2. Right? What's going to happen is that means that my 2 in the denominator on the left is going to go away. Now, the thing is, the reason why this is a little bit tricky is that a fraction bar is a grouping symbol, which means there is an invisible set of parentheses around the binomial in the numerator, the b1 plus b2. Normally, we don't need those parentheses, but the problem here is that if you multiply by 2 and you get rid of if you get rid of the 2, you're kind of getting rid of the fraction, right? That's what we're trying to do. We're trying to get rid of the fraction. But the b1 plus b2 still has this group around it. So if you do this method where you're just multiplying by 2, on your next step, you have to include those parentheses, which used to be invisible, but now they're not. So let that sink in for a second. The original fraction did not have parentheses around the b1 plus b2, or rather they were there, but they were invisible, right? We don't normally write them. But when we multiply by 2 in this context, we get rid of the fraction, but the b1 plus b2 is still being grouped together and then multiplied by h. So if you use this method, you have to include the parentheses there. Otherwise, it's wrong. This is not like an optional thing, okay? Continuing on, we're multiplying by 2, and so we have to do it to the right, and so 2 times a is simply 2a. Now, to get h by itself, notice that h is being multiplied by the entire thing. It's being multiplied by b1 plus b2. It's like it's one thing that's getting multiplied. So if I want to get rid of it, I simply divide by b1 plus b2, because that's a factor. When I do that, everything on the left is going to cancel except my h. So h equals, and then I have 2a over b1 plus b2, which, if you'll remember, is one of the two forms of our acceptable answer. And if you want to, you could pull out the a and get the first form. So no matter how you do 16, whether you do it in one step or two steps, you should still get the same answer. And honestly, both of the methods that we just discussed are, I think, equally mathematically valid. I think the first way is maybe a little bit easier, just because it's fewer steps. But it does require sort of understanding that when you multiply a fraction by its reciprocal, you get 1, and then when you multiply by 1, it just kind of goes away. So either method, feel free to choose whichever makes more sense. Last question is 18. So for 18, our formula is v equals pi r squared h, and our task is to solve for r. As I said earlier, every single one of these formulas has a geometric context. I'm not sure how familiar people are with this geometric concept. I don't think I can't actually remember whether we've gone over this one or not. If you recognize it, then that's great. The V here stands for volume. So that's a three-dimensional unit of measurement. It's the volume of a, if you know it, feel free to say it. It's the volume of a cylinder. There we go. Volume of a cylinder. So the volume is pi times the radius squared times the height. That's the radius of the circle that forms the base of the cylinder. And of course, volume is the amount of space, the amount of three-dimensional space that a three-dimensional object takes up. Again, all not necessary to solving 18, but I do think that the context is helpful. So we want to take this equation, we want to solve for r. We've got plenty of space to do it. So as always, my step 0 is to just flip it, so that and again, the reason I flip it is just to get the thing that I'm solving for on the left. Just tends to make things a little bit more organized. So we have pi r squared h equals v, and I want to get r by itself. So we have to deal with the pi, we have to deal with the squared, we have to deal with the h. Now, we're definitely going to want to deal with the pi and the h before we deal with the squared. So we're going to pause on the squared for a second and just focus on the pi and the h. Both the pi and the h are being multiplied to r squared, which means if we want to get rid of them, we can actually get rid of both the pi and the h in one step by simply dividing by pi times h. And again, the reason is because this is pi times r squared, times r squared times h. So because everything's multiplication, to undo that, we just do a division involving what we want to get rid of. So what ends up happening here is both the pi and the h on the left go away, which means we're left with just r squared equals. We have v divided by pi h. Well, I definitely can't do anything with that. I just have to leave everything the way it is, right? V is a variable, h is a variable, and pi is a constant. So that's not, nothing else is happening there. I want to get r by itself, and we're almost there, but we have r squared. I don't want r squared, I want r. So to undo squaring, we can take the square root of both sides, right? We're taking the square root of the left to get rid of the squared, and then we're taking the square root of the right because we have to maintain balance. So what ends up happening here is the left-hand side, my square root and my squared cancel, and I'm left with r. All right. Now, this is kind of an interesting situation. So technically, we need a plus minus here. And the reason that we need a plus minus is because if you look at the algebra, when we said r squared equals something, technically we didn't know whether that r was positive or negative, and we sort of lost that information when we squared it, because a positive squared is a positive and a negative squared is also a positive. So from a purely algebraic perspective, we need the plus minus because we are, quote, unsure as to whether the original r was positive or negative. So to account for that fact, whenever we sort of do this square root business to get rid of a squared, we have to introduce this plus minus to account for both of those possibilities. And then if we just continue on, everything else kind of stays the same, and it's v over pi h. And technically, that is our answer. I think I've said the word technically like half a dozen times. The reason I keep saying that is because, like I said, this is the volume of a cylinder, all right? Like, let's be honest. This is not some random collection of letters and numbers. Like, this is clearly the volume of a cylinder, and it just is, right? What that means is r is a radius, okay? And negative radius doesn't make sense, right? There is no such thing as a negative radius, or if there is, we don't care about it, all right? So even though the algebra tells us that we need the plus minus, if you did not include the plus minus, it kind of depends on your reason for not including it. If you did not include the plus minus because you recognize that this is the volume of a cylinder and that a negative radius doesn't make sense, that's actually fine, right? That's actually great if you realize that. However, if you did not include the plus minus because you just forgot about it and you you didn't know that you needed it from an algebraic perspective, that's less fine. So you can include the plus minus even though it's not necessary because it's volume, and we could go in circles talking about that for a while. But point is, our technically correct answer for number 18 is r equals plus or minus the square root of v over pi h.